Welcome back. In the last episode, we explored how frontal systems bring dynamic weather and how to identify them on charts. Now, we're going one level deeper. Today, we'll explore advanced pressure system phenomena, mountain waves, lee-side lows, and cyclogenesis. Let's get started. First up, mountain waves. These form when stable air is forced to rise over a mountain range and then oscillates downwind. The result? A series of rolling waves in the atmosphere that can stretch for hundreds of miles. Beautiful, but potentially dangerous. Mountain waves can create rotor turbulence, wind shear, and severe updrafts and downdrafts. The stronger the wind and the more stable the air, the more violent the wave activity. Pilots must be extra cautious when flying near mountain ranges in strong wind conditions. These waves are most common when winds blow perpendicular to the mountain ridge at 25 knots or more. You might see lenticular clouds, smooth, lens-shaped clouds that sit motionless in the sky. These indicate strong wave activity. Avoid flying directly beneath them. Let's talk about lee-side lows. These form on the downwind side of mountains, where descending air causes surface pressure to drop. The result? A localized low-pressure system that can cause wind to accelerate and weather to deteriorate rapidly. In regions like the Rockies or the Alps, lee-side lows are responsible for intense surface winds, sudden temperature drops, and shifting pressure patterns. These systems can form quickly and make flight conditions unpredictable even under otherwise clear skies. Now for cyclogenesis, the birth of a low-pressure system. It begins when contrasting air masses meet, usually along a frontal boundary. As warm air rises over cold air, pressure falls, and rotation begins. The Coriolis effect causes the system to spin. Cyclogenesis intensifies as upper-level divergence removes air from the column, encouraging more surface air to rise. This feedback loop deepens the low, tightens isobars, and increases wind speed. It's how storms develop and grow, sometimes explosively. When cyclogenesis occurs over land, it's usually driven by strong jet stream activity. Over water, like the Atlantic, it can lead to extratropical cyclones. These large, fast-moving systems can cover thousands of miles and affect entire regions for days. Let's not forget occlusion, the final stage of a mature low. When the cold front catches up to the warm front, the warm air is lifted off the surface entirely. The system loses energy and begins to weaken, but weather can still be intense. As pilots, why does this matter? Because pressure systems don't just exist in isolation. Their behavior depends on terrain, jet streams, humidity, and temperature contrast. If you understand the full picture, you can fly safer even in complex environments. Let's look at real-life examples. The Fohn wind in Europe is a classic mountain wave event, dry, warm winds on the lee side of the Alps, caused by air compressing as it descends. Great for gliders, tricky for powered aircraft. In North America, the Chinook is a similar phenomenon. These winds can cause temperature shifts of 20 degrees Celsius or more in minutes. If you see one coming, expect a sudden change in density, altitude, surface winds, and climb performance. Another key factor is pressure tendency. Rapidly falling pressure means a system is deepening, weather will worsen. Rapidly rising pressure suggests improvement. Your altimeter can show you what's coming if you know how to interpret the numbers. Always keep an eye on upper air charts. These show the 500 MB level and help forecast where cyclogenesis may occur. If you see strong upper-level divergence over a surface low, expect that low to intensify. Time to adjust your plan. Satellite imagery also helps. Look for comma-shaped clouds, a sign of a mature cyclone. These images show you the structure of the system, where the fronts are located, and where the worst weather is concentrated. It's a visual heads-up before you fly. Jet streams play a big role in shaping pressure systems. These narrow bands of fast-moving air aloft can guide storms, fuel their growth, or shear them apart. For pilots, they also affect ground speed and fuel planning, especially for transoceanic flights. Strong upper-level winds can make a low move quickly or intensify. If your route crosses one of these jet-enhanced systems, expect turbulence, wind shifts, and changing altimeter settings. Plan accordingly and check winds aloft forecasts. Another danger, low-level jets. These can form during the night and cause sudden wind shear on approach or departure, especially near pressure troughs or in warm sectors of a developing cyclone. Always check for LLJ advisories in your briefing. Flying near an active low-pressure system requires constant adjustment. Winds change with altitude. Visibility may drop suddenly. Icing and turbulence are more likely, but with good planning and constant updates, you can stay ahead of the system. Know your aircraft's limits. Be aware of alternate routes or diversion airports. Use GPS terrain and weather overlays. And above all, never chase a schedule into poor conditions. Pressure systems don't care about your ETA. Let's recap. Mountain waves cause dangerous turbulence. Lee-side lows form on the downwind side of terrain. Cyclogenesis is the process of storm formation. Jet streams can fuel or destroy developing systems. Terrain amplifies weather in subtle but serious ways. Understanding these advanced pressure phenomena makes you more than a weather reader, you become a weather strategist. You'll anticipate threats, adapt faster, and make decisions based on the full atmospheric picture. In our next episode, we'll continue with pressure systems, Part 4, where we'll look at how global pressure systems like the ITCZ, subtropical highs, and polar lows drive climate, winds, and seasonal flying conditions. It's the big picture view of aviation weather. See you in Meteorology number 08, Pressure Systems, Part 4.